Hi, my name's Dr. Billy Wu, and in this video we'll be talking about metal alloys and how we can use phase diagrams and a lever rule to help us understand their composition and properties. First of all, let's have a look at why metal alloys are an important class of materials. An everyday example might be coins. Now, if we think about what are the material requirements, there's a number of key considerations. First of all, there's a number of different coins and we want to be able to distinguish one from another. Secondly, security. We obviously want to make these coins difficult to counterfeit, but at the same time, we want these to be easy to manufacture. When in use, we also want these coins to be wear resistant and have a high corrosion resistance. Finally, we also want them to be antibacterial. In terms of the last criteria, copper has natural antibacterial properties, which is great. However, it's very ductile and soft. But what we can do is we can alloy this metal with another metal to change its properties. The €2 coin, for instance, has two different alloys, an outer ring made of 75% copper and 25% nickel, which is silver in color, and an inner section with 75% copper, 20% zinc, and 5% nickel, which has a gold color. The €1 coin has the opposite of this, and the 50, 20, and 10-cent coins are made up of an alloy of 89% copper, 5% aluminium, 5% zinc, and 1% tin. Combined, this is called Nordic gold. The 5, 2, and 1-cent coins, on the other hand, are copper-plated steel, since we want to reduce the cost of these low-denomination coins. If the value of the metals were greater than the stated value of the coins, then people would just collect these and melt them down, which is obviously not what we want. Now, if we look at what options we have for material selection, the periodic table gives us our basic building blocks. This consists of over 100 elements, which might sound like a lot, but many of these are either scarce or would be unsuitable in most material selection problems, thus limiting our options. However, if we mix elements together or alloy them, this allows us to augment the material properties and opens up many possibilities. The types of elements that we alloy together, their proportions and processing conditions have a huge impact on the eventual properties. Let's take for example bronze. This is an alloy of copper and tin, and it's relatively hard and resists corrosion, which makes it ideal for making statues. However, if we change tin for zinc, we can then make brass, which is softer and more malleable, making it suitable for manufacturing musical instruments. Therefore, you can see that alloying materials has a strong influence on its material properties, and phase diagrams can help us understand what's happening. So now let's look at a few basic concepts which we'll be discussing in more detail throughout the video. Firstly, the term alloy refers to a mixture of a metal with one or more other metals or nonmetals. We term this binary when we have two elements and ternary when we have three, and so on. When talking about a component, we're referring to an element in the alloy. A phase is a region of a material which has uniform physical and chemical properties. This is an important concept that we'll come back to later on. In the image that you see here, this is an optical micrograph of steel, which is an alloy of iron and carbon. The different colored grains you see here are different phases. The composition of a phase is the mass of each component in the alloy or phase. The constitution is the sum of the phases, the mass of each phase, and the composition. And finally, the phase diagram is the equilibrium constitution of all of the combinations of temperature and composition for that particular alloy. Now, given that this video is about phase diagrams, it's worth discussing in a bit more detail about what a phase is. Earlier, we defined this as a region of a material which has uniform physical and chemical characteristics, but let's have a look at an example to help us visualize this. The plot you see here is the phase diagram for H2O, where the x-axis is temperature and the y-axis is pressure. Now, we know at room temperature and atmospheric pressure, H2O exists as a liquid state known as water. As we decrease the temperature below 0 degrees C, the H2O undergoes a phase transformation from a liquid to a solid we know as ice. Clearly, the physical properties of water are very different to ice. If we then increase the temperature to above 100 degrees C, the ice transitions to a liquid and then to a gaseous steam. Again, steam has very different physical properties to ice and water, but it has the same composition. So what this tells us is that temperature is very important when describing the physical properties of a material. Now, when we start to mix different elements together, a number of different things can happen. If the two elements are similar to each other, they can form what we call a solid solution. A solid solution is a single-phase region in which the solute atoms have mixed with the solvent atoms to form a homogeneous composition. The term solute atoms refers to the elements in the smaller proportion, and the solvent atoms refer to the element in the larger proportion. If the two elements are very similar to each other, they can have complete solid solubility, which means the solute atoms are completely soluble in the solvent atoms for any composition of the solute and solvent atoms. A second phase therefore does not form. In order to visualize this principle, let's take the example of a copper alloy. Here you can see a cartoon which represents the copper, which is the solvent atom in this case. We then want to alloy this with nickel, which is the solute in this case, since there's a smaller proportion of this element. In the case of copper and nickel, they have complete solid solubility, and therefore for any amount of copper or nickel, they'll form a homogeneous phase with uniform physical and chemical properties, as shown in the diagram. If we dive a bit deeper into alloys which have complete solid solubility, we can start to see the utility of the phase diagram. So let's look again at a nickel-copper alloy example, which exhibits complete solid solubility. From our earlier example with H2O, we know that temperature is a key metric for determining the phase and physical properties of a material. In the case of nickel, the melting point is 1453 degrees C. Copper, on the other hand, has a lower melting point of 1084 degrees C. Now, if we draw the equilibrium phase diagram for the copper and nickel alloy, it looks something like this. On the x-axis, we have the composition in terms of weight percentage of nickel, and on the y-axis, we have temperature. We can also see several lines which represent the phase boundaries between different regions. Here, we've got three distinct regions: a single-phase liquid region, a single-phase solid solution region, and a two-phase region. Given that this is a binary alloy of two metals, copper and nickel, when the weight percentage of nickel is 0, this means that we've got 100% copper. And when we have 100% nickel, we have 0% copper. Now, if we assume we have an arbitrary composition of nickel and copper, where the temperature is above the melting point of nickel, we'll be in a single-phase region where the structure will look very homogeneous. Given that we're using the term phase quite a lot, it's useful to remind ourselves what that actually means. So a phase is defined as a region of a material with uniform chemical and physical properties. So at this temperature and composition, everything will behave like a liquid. As we cool the alloy, the overall composition stays the same, but then a solid phase starts to precipitate out of the liquid. As we continue to cool the material, we can see that eventually all of the liquid becomes a solid, where the grains which initially started to form have grown and joined together. Where these grains join are what we call grain boundaries. So that was the situation where two metals have complete solid solubility. However, in many cases where the two metals are considerably different from each other in terms of atomic size and charge, complete solid solubility isn't possible. Limited solid solubility therefore means the solute atoms aren't completely soluble in the solvent atoms for any composition, and therefore a second phase often forms. Now, let's have a look at the example of aluminium and copper. These two elements don't have complete solid solubility. However, at low concentrations of solute atoms, a solid solution can still form, as shown in the diagram. However, as the concentration of solute atoms increases in a limited solid solubility system, a second phase can precipitate out, as this is more thermodynamically stable. Here, you can see in the diagram that as we add more copper, a different phase has formed where the composition and structure has changed. Now, this can seem a little bit abstract, so let's have a look at an example of a limited solid solubility system which you might come across in your everyday life. Here, let's take the example of adding sugar to water. The plot on the bottom shows the phase diagram for a mixture of water and sugar. The x-axis is the weight percentage of sugar, where 0% sugar is 100% water, and vice versa. On the y-axis, we have temperature, and we can also see two regions. Initially, at low concentrations of sugar, this dissolves completely to form a single phase syrup. However, as we add more and more sugar and pass the 65% solubility limit, the liquid can't hold any more sugar and solid sugar starts to precipitate out, leaving us with a two-phase system of liquid syrup and solid sugar. Now, if we return back to our binary metal alloy system and look at silver-copper alloys, which have limited solid solubility, this is what the phase diagram looks like. This is obviously a little bit more complicated than the phase diagram for the complete solid solubility case, but we can break this down into more digestible parts. Here, we have three single-phase regions. Firstly, at low weight percentages of silver, we form a solid solution with silver as the solute, which we term alpha. Now, the naming convention here is somewhat arbitrary, and in reality, we could have called this anything else. Then, at high silver concentrations, we have another solid solution region where copper is the solute, which we term the beta phase. At high temperatures, we then have a pure liquid phase where everything has melted. Beyond these single-phase regions, we also have three two-phase regions, where firstly, we have a two-phase region of alpha and liquid. Then, we have a two-phase region of beta and liquid. And finally, a two-phase region consisting of solid alpha and solid beta. The lines on the phase diagram mark the boundaries between where these phases form, and each of these has a different name. The liquidus line, for instance, represents the temperature and composition at which all components are liquid. The solidus line is the boundary beyond which no liquids form. And the solvus line is the solid solubility limit between the alpha and beta phase regions. We also have a region called the invariant point, where the liquidus lines meet, as shown by point E on the plot. Now, if we focus on this phase diagram and visualize the equilibrium microstructures which form, this will help us understand what's going on. If we select a low silver composition and start with a high temperature, we can see that we have a pure liquid phase. Then, as we decrease the temperature, we go through the liquidus line into the two-phase alpha plus liquid region. Here, the microstructure looks a bit like a soup with bits inside. Then, as we cool the material further, we pass through the solidus line where all the remaining liquid has turned into solid alpha. Finally, if we continue to decrease the temperature, we pass through the solvus line, where the beta is no longer stable in the material and starts to precipitate out into a second phase. This type of microstructure with two phases can impact the mechanical properties of a material, since it can affect how easy it is for atoms to slide past each other. So that was useful to get a qualitative view on what's going on in the material as we cool it. However, if we want to quantify the amounts of each phase in the two-phase region, we have to take a slightly different approach. In this case, we can use something called the lever rule. To run through this example, let's start again with a simple complete solid solubility system. First of all, we start by drawing a horizontal tie line at the temperature of interest in the two-phase region. We then mark the overall alloy composition on this tie line, which we've arbitrarily put at 50% nickel. If we want to calculate the fraction of one phase, we do this by taking the length of the tie line from the overall alloy composition to the phase boundary of the other phase, and then divide this by the total tie line length. This equation is given at the bottom for the generalized form describing the mass of the liquid and the mass of the solid in this two-phase region. If we now put in some numbers to help us visualize what this actually means, let's assume we have a 50% concentration of nickel, which means we have 50% copper in our alloy. At this arbitrary temperature that we picked, the liquid-solid phase boundaries occur at a 20% and 80% nickel composition. If we then take the equations for the mass fraction of solid, we can see that the length of this tie line from the overall composition to that of the phase boundary is 0.5 minus 0.2, giving us our numerator. The length of this tie line is the composition of the solid phase boundary minus that of the liquid phase boundary. This acts as our denominator. If we then take the ratio of these two, we can see that the mass fraction of the solid phase is 50%. We can then repeat this process for the liquid phase, which should also be 1 minus the solid mass fraction. Now, let's say for example, we increase the amount of nickel in our alloy to 80%. When we then put the numbers into our equation, we can see now that we have 100% solid and therefore 0% liquid. This makes sense since we're now at the solidus line where the entire alloy should be in the solid phase. Conversely, if we reduce the amount of nickel to 20%, we can see that the mass fraction of solid becomes 0 and therefore we have 100% liquid. This again makes sense since we're now at the liquidus line composition and highlights another important factor, that alloying metals allows us to control the melting point of the alloy. So hopefully that example of the lever rule helps you understand how to use it. However, it's also useful to know how this is derived so that we don't just take it at face value. Now, to do this, we firstly take a mass balance of our two-phase alloy, which consists of a solid phase and a liquid phase. Since there's only two phases here, the sum of the two must equal the total mass of the alloy. Next, if we assume an arbitrary alloy composition of X% nickel, we can say that the mass of nickel over the mass of the alloy gives us our mass fraction of nickel. If we rearrange this equation to make the mass of nickel the subject and then substitute the equation in for total mass, we get a description of the total mass of nickel in the system. Now, if we create an independent mass balance for nickel, what we can say is that the total mass of nickel can be described as the mass fraction of nickel in the liquid plus the mass fraction of nickel in the solid, since these are the only two places where it could be. It's important to remember here at this point that nickel generally exists in both the solid phase and the liquid phase. We now have two independent equations which describe the mass of nickel, and if we equate the two together and rearrange them slightly, we come to this equation. Finally, if we say that in the two-phase region, the mass of liquid and the mass of solid equals 1, we can then solve the equations for the mass fraction of liquid and solid. So now that we've done an example of how to use the lever rule for a complete solid solubility system and also understood where this comes from, let's look at our final example where we apply this to a limited solid solubility system, such as silver and copper. Let's say, for example, we have an alloy consisting of 40 weight% silver and 60 weight% copper at 600 degrees. Now, the first question might be, what are the phases that are present at this temperature and composition? This is relatively straightforward, as we find the composition and temperature that we've just mentioned, and then look at what region we're in the phase diagram. In this case, we can see that this is in the solid alpha plus beta two-phase region. Now, whilst we know at 40 weight% silver and 600 degrees, we have two phases, what we don't know is what their compositions are. To answer this, we can use the lever rule. First, we draw a tie line at 600 degrees between the alpha and beta regions. Then, if we read the composition of alpha at the solvus line, we can see that we have a composition of 4% silver and therefore 96% copper. Since this is the point where we only have alpha, we can say that this is the composition of alpha. We can then repeat this process for the solvus line between the alpha plus beta region and the pure beta region. Here, this tells us that beta has a composition of 97% silver and therefore 3% copper. Okay, so now that we know we have two phases and what the composition of each phase is, the only missing element is now calculating what are the mass and volume fractions of each of these phases. To do this, let's first introduce a few definitions. C1 is the overall alloy composition, W alpha is the mass fraction of alpha, and W beta is the mass fraction of beta. We can then use the lever rule equation to calculate the relative amounts of alpha and beta, which are 61% and 39% respectively. This looks slightly different to our earlier implementation. However, it's actually the same since we just replaced liquid and solid with alpha and beta. Great. So now we know the mass fractions. The final step in the calculations is to find the volume fractions. This requires us to revisit the amount of each element in each phase and to take an average of their densities. Here we define CAg alpha as the concentration of silver in alpha and CCu alpha as the concentration of copper in alpha. The density of silver is taken as 10.49 grams per centimeter cubed, and the density of copper is 8.96 grams per centimeter cubed. Since we know the concentrations of each component and their densities now, we can calculate the overall density of each phase by using the equation below. If we then put the numbers into the equation, we can see that the density of alpha is 9.01 grams per centimeter cubed, and that of beta is 10.44 grams per centimeter cubed. This makes sense since alpha is copper rich, which has a lower density than silver, and beta, it has more silver in it. Also, it's worth doing a quick check to see if the resulting densities are between that of the two base metals. Finally, now that we have the densities and mass fractions, we can calculate the volume of each component. If we take the ratio of the volume of a single phase and the combined volume, this then gives us the volume fraction of each phase, which are 0.64 and 0.36 for alpha and beta respectively. So, to summarize, hopefully you've seen that alloys are used in a range of applications, but changing their composition can drastically change their physical and chemical properties. Phase diagrams are a tool which can help us to understand what sorts of structures they should form at different compositions, where a phase is a region of a material with uniform chemical and physical properties. In cases where the alloying elements are similar to each other, they can have complete solid solubility where any proportion of solute atoms are soluble in the solvent atoms. However, in cases where we're using relatively dissimilar metals, we can have the case of limited solid solubility, where the solute atoms aren't completely soluble in the solvent atoms and another phase forms. Through using the phase diagrams, we could then see how different temperatures and different compositions give rise to different microstructures. And finally, we applied the lever rule to help us to quantify some of these changes that we've seen. So hopefully this video was a useful introduction to metal alloys, phase diagrams and lever rule, and thank you very much for listening.